is poisoned with an address of a bad function. Let's just say the address is oxdeadbeef, and you land in this other function where you can do whatever you want. But the question that might be running through your mind now, or I hope it's running through your mind, is, hey Joe, in your handler function, you're calling the function you're trying to hook. So shouldn't that be an infinite loop? It turns out that's not, because if you remember from earlier, each dynamic object that you load into your process has its own set of data. So each dynamic object has its own set of PLT entries and its own global offset table. So as long as you poison everybody else's except for the got PLT section of the library that includes your bad code, as long as you don't poison your library itself, then you'll be okay. Dynamic linking will happen normally for you. You just have to overwrite everybody else's shit. Okay, so what about Mac OS? We just described how it works in ELF, but what about Mac OS? Well, it's not quite like comparing apples to oranges. It's actually really similar. This is the graphic that I was talking about that's like super sexy that I spent a lot of time drawing. ELF is on the top, obviously, Mac OS is on the bottom. The instructions, the actual assembly instructions that are generated are exactly the same. They're just rearranged, right? So on ELF, you have a jump instruction followed by invoking the dynamic linker, as we saw on the other slides. But on Mac OS, they just put all the jump instructions together and then all the dynamic linking invocation functions together. So they just kind of rearrange stuff, but it's exactly the same thing. It works exactly the same way. Okay, so we know how to hook two types of functions, but there's a third type that also matters, inline functions. And this is actually really fucking tricky. We can't hook, there's a function that I needed to hook to build this memory profiler called add FreeList. But the problem with trying to hook add FreeList is that it's marked as inline, which means that the compiler has the option of inserting the instructions for this function directly into whoever is calling this function. So if that happens, you won't actually see any explicit call instructions in your binary. So what do we do now? Are we jacked, or is there a way around this? Well, it turns out that if you look closely at this generated code, you should notice something. You notice that there's this identifier called FreeList, and FreeList is getting updated to point to the new head of the FreeList as objects are recycled. Notice that FreeList isn't defined in this function, so it has file level scope. So what about a crazy stupid idea? Since FreeList has file level scope, it lives at some static address, right? Add FreeList updates the FreeList by just inserting something at the head of the FreeList. Why not just search the binary for all move instructions that target FreeList and just overwrite all of those? And it turns out that might actually work, but there are a few problems. The system isn't actually ready to make a call instruction at that point. What does that mean, not ready? Well, remember before we talked about the ABI and how the ABI talks about alignment and calling convention? Well, it's not quite ready to call a function because there was just a bunch of move instructions. If we just implant a call instruction, there's no guarantee that the stack is aligned or that arguments are in the right registers. So what do we need to do? Well, it turns out that we can actually use another type of instruction instead. We can actually just use a jump. We can insert a jump instruction, transfer execution to an assembly stub that we generate at runtime, and then recreate the instruction we just overwrote, set the system up to call a function, and then do whatever we're going to do, whether it's good or bad or whatever, and then jump back and resume execution as if nothing happened. And this is sort of like the crusty third hook that you need to pull this off. So there's a checklist of things we need to do. We need to save and restore any registers. We need to align the stack. We need to regenerate the instruction that we're overwriting. We need to arrange for any arguments that we care about to end up being put in the right register so they get passed to the function. We need to invoke our code that does whatever it's going to do. And then we need to resume execution as if nothing happened. So here's an example of an instruction that is updating the FreeList that we're going to overwrite. So this is just saying, hey, I'm going to take RBX and I'm going to write it to the top of the FreeList. So we can't put a call instruction there because, as we said, the system is not ready to make a function call. The stack isn't aligned, arguments aren't in the right place, everything's all fucked up. So what we can do instead is we can just insert a jump instruction. So it turns out that the move instruction is 7 bytes. The jump instruction, including the offset, is only 5 bytes. Since we can't grow or shrink the binary, we have to insert 2 NOP pads just to make everything work out. So this address right there, that's just the address of the assembly stub we're going to transfer execution to. And when the assembly stub finishes, we want to return back to this NOP and then just fall through and continue executing as if nothing happened. So here's a shortened assembly stub that actually does this. This is an assembly stub that when I ran my code, This was generated at runtime. It has to be generated at runtime because this first instruction up here at the top, this is getting overwritten, and who knows what it's going to get, who knows what that instruction is going to look like when your Ruby binary is actually running in memory, right? Like everybody compiles their own Ruby, and so this could, instead of using RBX, who knows, maybe you're using RCX on your Ruby binary. So you just search for anything that targets the free list, you overwrite it with a jump, and then you have to regenerate what you overwrote on this little trampoline here. This is actually shortened. The real thing is way, way longer and way uglier. But I'm going to provide a link to the code later. That way you can actually check it out if you want to see what the deal is. So yeah, we need to recreate the instruction we overwrote. We need to save a register so we can pass our argument. So I'm just going to save RDI. That's where the first argument lives, if you remember from earlier in the talk. We're going to move the free list into RDI because for a memory profiler, I want to know who just got freed. That way I can track information about them. I'm going to save RBX because I'm going to fill it with a value in a minute. I'll align the stack to comply with the ABI. And then I'll move the address of a handler function into RBX. That's why I saved RBX a few instructions earlier. I'll call my handler function indirectly via RBX, and then the handler function will just do whatever, something good or something bad, whatever you want to do. You do a bunch of cleanup, and then you just jump back to wherever you overwrote the instruction originally. And the crazy thing about all this hackery is that when you're done, it actually works. You can actually use this, like if you have Ruby and you care, you can gem install MemProb and you can actually use this thing. And all the code that hooks these three types of functions exist in this Ruby library that I built called MemProb. So you can go on GitHub, you can read the code, and it's real. And it's actually pretty powerful. These three things can be used to build lots and lots of really interesting tools. So just to give you like a quick rundown of like some of the cool things you can do with this. So, we can do stuff about memory, right? Like I can write this Ruby code. I can say, hey, include my memory profiler, start profiling, run a bunch of code and give me stats. And I'll get stats like this. Like I can find out on the exact file and line number where objects are being allocated. So if I have a memory leak, I can look and I can say, hey, on file 1.rb on line 25, I'm creating 1 million objects. So I can know exactly where things are leaking, which is pretty fucking sick. So the text-based output is cool, but it's really painful to grok. So my roommate Aman built a web UI for this thing, so you can like actually traverse stuff and you can learn all kinds of crazy information. You can find who's holding references to what other objects, where you're leaking memory. You can look at like the inheritance tree of objects. You can look at the subclasses of string in Rails. You can explore the socket hierarchy. You can do all kinds of stuff. You can find like massive arrays. And since in Ruby all Ruby code is actually just stored on the heap, I can actually just go and regenerate Ruby code from using these function hooks, right? Because I can just grab these things when they're getting created and I can just reverse them back into Ruby code, which is pretty cool too. You can go and look through Ruby standard library and you can say, oh, look at these like really bizarre functions that exist in Ruby. You can see, if you have sockets open to any web services, you can see what you're connected to on what port. And that's all pretty cool. There's also performance information too, right? Like you can find out, how long requests take, which Rails controller you hit, request information. You get crazy stuff too. You can track MySQL queries, right? Since I can hook into anything, I can track anything I want. I can track like MySQL queries, how many I make, how long they take. I can track the garbage collector, how many calls there are to the GC, how long these calls take. I can track how many objects are created in general, which is pretty useful as well. And that's all cool, but what about some evil things we can do instead, right? I mean, the performance stuff is cool, but maybe you don't care about performance. So you can build a library that does something evil, but you'll need a social engineering aspect of it because you need some way to get people to actually use your library. In a few slides, we'll talk about how to actually get around this so you don't actually need to social engineer. But for right now, we can build a library that will do something bad, but we need to just convince people to use it. So how would we do that? Well, evil lives. I built an evil version of MemProb. The branch on GitHub is just DNW. That stands for do not want. If you try to build it, it will fail. I put a bug in the makefile. That way nobody can accidentally go screw themselves by building this. And the way that I would social engineer somebody to use this is I would say like, hey bro, this makes Ruby faster. And it does make Ruby faster because what it does is it hooks the read system call. It looks for a magic cookie. In this case, the magic cookie is just my name, Joe. And then it just disables the garbage collector. The result is Ruby is fast. But it is now a time bomb, right? Eventually it'll eat all the RAM on your system and your system will melt down. And if you really want to drill it in, like, hey, it makes Ruby faster, like, look, here's a bullshit benchmark, but just don't tell them it's bullshit. But look, here's normal Ruby, and normal Ruby takes 7.5 seconds to just do the stupid benchmark. 26 requests per second. Then after you use this thing that makes Ruby faster, suddenly you shave off a second off the time, and you're now up to 30 requests per second. So you show this to a Ruby developer, and they're like, dude, I need this right now. So anyway, this example is stupid, but the whole point is just a proof of concept. You can do anything, right? Like you could hook read and write and just phone home with all the data coming in or leaving the application. You can fork a backdoor when you see a specific cookie. You can do whatever you want. But the shitty thing is that we have to social engineer, and that's kind of a problem. This guy also has a problem, unrelated to social engineering. So the problem with social engineering, at least from my perspective, is that it's painful, and I don't want to have to social engineer things if I don't have to, like if there's a way around it. So it would be cool if there was a way to inject these evil libraries into running processes without having to convince people to download my thing and look at some bullshit benchmark. It turns out that there is a way of doing this. There is a project written by this guy called Sean Clowes or something. It's called Inject S0. It injects libraries into running processes using Ptrace. This hack is actually super, super clever. To borrow a very awesome internet meme, fucking magnets, how do they work? I want to know how Inject S0 works because it's pretty cool. It's actually pretty simple. It just uses Ptrace. Ptrace allows you to view and modify the register set and address space of another process. Any permissions that are set on the memory in that process are ignored. So even if a page is marked as read-only, you can still write all over it or do whatever you want. So the way Inject S0 works is it just attaches to a target process using Ptrace. It saves a copy of a small piece of the program stack, saves a copy of the register set, and then it creates a fake stack frame with a saved return address of 0. You then set the register set to point to DL open. So you have the instruction pointer pointing to the address of DL open. You set up the arguments, so you have the path to the shared object, the mode stored in RSI, and then you just let it rip. Okay, so you wait pit, and then eventually it'll segfault, because once DL open's done, it'll load in this library that you want it to load in, and then it'll segfault because the saved return address is 0. When the segfault happens, you as the tracer of the process will get a signal. So the child process will get suspended. You'll be awoken, and you'll be allowed to do stuff to it. So you just restore the stack, restore the register set, and just let the world continue let the world continue on its merry way as if nothing bad happened. And this actually works, and it's pretty cool. But there's a couple downsides. There's downsides to both aspects of the Ptrace method and the evil DSO method. Remote allocating memory is a pain in the ass. It's doable, but it's just really painful to do. Generating segfaults and running processes might be bad. Perhaps the system administrator has some alert thing set up so that if a segfault happens, then they get an email. I have that set up on my boxes, so if I get a segfault, I know that something bad happened. And binary patching in general is hard to do. Like the stuff that we just talked about earlier, the 3 types of function hooking, those things are complicated. And it's possible to do with Ptrace, but like adding another layer of difficult in between you and actually doing what you want to do is no fun. So doing it with binary patching is hard, but doing it with Ptrace just makes it harder. The problem with the evil DSO though is getting the user to use your library might be hard, and already running processes will need to be killed and restarted, which also sucks. And you need to poison the app each time it's started. And in general, binary patching is hard. But what if there was a way to bootstrap the process, right? Like what if we can just combine both methods? Like we can just use Inject S0 to load the evil DSO, and then the evil DSO will just take it from there and do a bunch of, do all the crazy binary patching stuff. So in order to do that, we needed a 64-bit version of Inject S0, but it turns out that the Inject S0 that I talked about by that dude Sean is only 32-bit. So I was getting ready to write a 64-bit port, and then I searched the internet a bit, and I found that this guy Stealth ported Inject S0 to 64-bit boxes. This is his blog post releasing the source code. I did a bunch of trivial cleanup on it because it was a little bit old and it was suffering from some bit rot. So I did some minor cleanup, and I put the code on the GitHubs. So if you want to copy that, you can go there and check it out. I tested it on a 64-bit Ubuntu VM, and it actually works. So I can use Inject S0, and I can inject my stupid thing that looks for the string Joe and disables the garbage collector, and then it DOS's my box. So it's pretty cool because I had this web server running, and I just used Inject S0 to infect it, and then all hell broke loose after that. I was going to try to demo that, but then I wouldn't be able to give the rest of the talk. So I can't demo that. So anyway, using those 2 things, I don't know, I think it's kind of cool. I don't know if it's a jackpot or not, but it's definitely pretty sweet. So we talked about some attack mechanisms. So what are some defense mechanisms to protect against this sort of thing? Like I said earlier, I'm not a security researcher, so I don't know like, all the up-to-date, like amazing defense mechanisms that are out there. But what I do know for sure is that everything's a trade-off. So there's a trade-off between defense mechanisms that are difficult to implement, difficult to understand,